We've recently discussed definite integrals as area, and now we're going to consider a special type of area problem. So let's suppose that we have the function f of x equals 2, and we know that this will give us the graph of the line y equals 2. And you do need to notice that f of x equals 2 is really no different from f of t equals 2 or f of k equals 2. Right? The input variable we use really doesn't matter. The shape of the graph will not change. We will still have a horizontal line at 2, regardless of if it's f of x or f of t or f of k. Now, hopefully it will make some sense on why we might consider using f of t, though. Let's consider what this expression means. The integral from 0 to x of f of t dt. Well, this is a function, and as x changes, so does the value of the integral. Here's what I mean. If you were to consider this thing from 0 to 0 of f of t dt, you would get 0. There would be no area to consider. But from 0 to 1, this is now changed to 2. And from 0 to 2, this is now changed to be 4. And if we went all the way to 5, the value of our original expression is now changed to 10. Right? In this particular case, as x gets bigger, the integral increases as well. And a way to think about what's happening, or to talk about it, is that we're accumulating area. Right? I'll do this in red. At first we don't have any area. We were just thinking about this. Then we went out to 1, so we accumulated an area of 2. Then we kept going. We went to 2, and we accumulated some more area. Then we went all the way to 5, and we accumulated some more area for a total of 10. And so that's why, since we're just accumulating area, we sometimes reference this as being the accumulation function. Right? We're just accumulating area as we change the value of x. Right, now, the reason we use f of t is to think about this change as it happening over time. And this 0 to x of f of x dx would also be very confusing, because these aren't exactly the same. So, with that in mind, let's take this a step forward. Let's say that big f of x, I'll do this in black, is equal to the accumulation function 0 to x f of t dt. And all of this is related to the graph that I will sketch below. And so I want you to think of, since this is the graph of y equals f of x, little f of x, I'm going to tell you that this is the rate of snowfall over time. So at x equals 1, the snowfall's value is 3. It's snowing at 3 units 3 inches per hour. We'll use inches per hour. And at 4, which will be here, it is not snowing. It is snowing at a rate of 0 inches. Or no, at 3, it is 0 inches per hour. And at 4, the snow is melting at -4 inches per hour. So if we want to consider what's happening, the way that snow is accumulating as time passes, let's fill out this chart. As x changes, we'll consider what's happening to big F of x, how much snow is accumulating. So take a moment and fill that out, pause the video, and then unpause it to see what. And you should have gotten this table if you paused it. And notice that we can see that the snow increased until time 3, and then it decreased, and then it increased, and then it decreased again. That's how much snow, total snow, at a time. Right? It's assuming some had melted, more had fallen, none had fallen at certain times. And now we can ask a different question. We can ask about this. If f of x equals that integral, then the derivative of big F of x must equal the derivative of that integral. Right, we're just taking the derivative of both sides of that original equation. And the question you should ask is, well, if you took the derivative of an integral, what would you expect to happen? Well, you should expect those things to cancel one another out. They're inverse properties. So f prime of x, the derivative of the integral, is the same thing as saying that f prime of x equals f of t dt. And if that's true, then we really should be able to fill out a table of values for that as well. So pause the video, think about that, get it straight in your mind, and then fill out the table. So if you pause the video, you should have gotten these values. Notice it's exactly the table, or the graph, because that's the derivative. And so then we can ask questions like, on what subintervals from 0 to 8 is f increasing? Well, f would be increasing on this interval from 0 to 3, because the derivative is positive. And when it's decreasing, well, it's decreasing here from 3 to 5. It's increasing from 5 to 6.5, and it's decreasing from 6.5 to 8. Where in the interval does f achieve its minimum and maximum value? Think about that for a moment. Well, the only places that mins and maxes can occur are at endpoints and at changes in derivative. So I would want to consider what's happening. I'll mark these in red. What's happening at 0, that's an endpoint. What's happening at 3, because it changes from positive, the derivative changes from positive to negative, so there could be a maximum there. At 5, there could be a minimum, because the derivative changes from negative to positive. There could be a maximum at 6.5, because the derivative changes from positive to negative. And 8, because it's an endpoint. And we can see that the minimum occurs at 0, the endpoint, and the maximum occurs at 3. And we can see that here. There's the maximum, and here's the minimum in the original function table. Right, and the maximum value is 6.5 inches, and the minimum is 0 inches. We could ask a question about the concavity of the original function. Any points of inflection? What would those be? If you haven't, pause the video and think about it and write some stuff down. Let's talk about concavity. The graph would be concave up when the derivative is increasing. So that will be here. Point of inflection will be when the derivative is 0. So that would be here. Because it's not increasing or decreasing. Concave down when the derivative is decreasing. Now it's increasing. It'll be concave up here. It changed right there. Right, it's still concave up. Concave down. Right, we can see these changes. Based on that, we could sketch a rough graph of big F of x. If you haven't, go ahead and sketch a rough graph. Right, it may look something like this, where it's increasing to its maximum, changes concavity, it's decreasing, increasing again. Just a rough graph based on what we're seeing. In part 2 of this section, we'll look at another example using a similar graph.